One thing I always like to do is get a graphing calculator my whole life when they started coming out when I was a teenager, and playing with graphs. And one of the most amazing ones, the first ones I played, was with the Maclaurin series, or well, more generalized as the Taylor series. And Google now, if you type y equals something in terms of x, will graph it, and if you go comma another one, it'll graph both of them, right? So I have up here sine and cosine, which of course are the same thing, just phase shifted. So when you hear about phase and stuff, it's a phase shift between those two. It's the same thing, but just shifted. Okay. Oh, I might misspeak if I go into there too much. So here's an interesting thing. This is a place that'll expand with the Taylor series. Now the Taylor series, using calculus, you can take derivatives of your function, and you can approximate any function to whatever degree, to whatever degree you want, right? With some number of terms in your Maclaurin series. So let's look how it works. So let's say we go to the power of 5 here. Okay. So if first I try to go to the power of 2, there is no even component. See, here's the equation. So let me just obviously let's chart this as its first approximation with to the first power, x to the 1. Let's see how good of, okay, it matches the slope. Okay, a little bit there. This is not accurate because the scale. I hate that it does that. I wish it did equal scales. Yeah, there. Right? And now we'll zoom that out. Okay. I don't know if you noticed what I did there, but the scale, x and y scale, wasn't the same. So here. Okay. So that's its first approximation. Its second approximation with x squared, well, there is no x squared. X squared doesn't help because of the shape of this. It likes only odd powers. So I don't know if you've ever looked at this. Now I'll take with the next term, which is the third term. Let's do that. Didn't I do that? Okay, here we go. See. So this has 2 terms in it, but see, there's the coefficient of the x squared term happens to be. So let's see how this goes. See? It makes, on x to the 3rd type curve, it starts to look like that. And if I add the 5th, so it's plus, right? So it's plus. See? Now it's starting to match that little curve there. Look, if I go up to 10, it'll just start wrapping more and more of that. I just think this is so fucking fascinating. And the thing is, you can do the same thing the other way around. You can make functions out of sine waves that will track a non-sine wave, that'll track, x squared or whatever. We'll show you that later, maybe. So let's get out to 10. And I'll put that whole thing in there. Notice the even factors are not there for this kind of shape. And you can do this with any function, not just sine. Just any function. This is an amazingly powerful thing. Okay. See? Now it's wrapping it further. It takes a lot of terms. But if it went up to 100 terms, it'd start wrapping this. Infinite terms, it would wrap the whole function. I just love that. Let's just be ridiculous for the final moment here and see if I go up to 100 terms. This will be fine, but I don't think Google will like 100 terms. Oh, it won't go up to 100. So let's do 30. Let's see how far 30 will go. Or 50. Let's see if it'll be 50. 50 terms, which will actually be 25 terms. Okay, so let me try to get That's a lot of terms. Okay, maybe we shouldn't get all of them. Let's just go out to, here we are, x to the 41. We'll stop with that. This might take a while. We do. Didn't see. Oh, there we go. Yeah. See? With that many terms, it's wrapping exactly. So you can even see the red line. Mapping exactly. The values are exactly mapped. And then finally out here, it's like, oh, I lost it. God, you gotta love that. And you can do it the other way around. Next time I'll show it the other way around using the Fourier transform. You're welcome.